We're now going to have a look at two more very famous, very powerful, very effective methods for checking on the convergence or divergence of a series. And of course, as you can imagine, these kind of roots have nothing to do with it, even though we're trying to put them into a ratio. But no, that's not the kind of roots we're talking about. Ratios, yes, we're talking about fractions. Roots, we're talking about, well, not quite square roots, but general roots, as we're going to see in a minute. Okay. Now, what are we going to achieve, or are we trying to achieve with these tests? Well, remember that we have the integral test, and that's fine and dandy, but it requires us to compute an improper integral. So we have to move from the given series to an integral, and then hope that that integral actually works out. Then we've seen comparison tests. They're also nice and dandy, but they also require us to compare the given series to another suitable series that we can use as benchmark. Okay? So the question is, well, is there some tests that only use the given series, that don't force us to go somewhere else to look for convergence or divergence, so either to an integral or to a different series? The answer, of course, is yes, otherwise we wouldn't have this topic at all. And the answer to this question is, in fact, the ratio and the root tests. So let's see what they look like. Let's start from the ratio test. As I said, this is a very common ratio whenever you're using infinite series in any applied situation. You're trying to figure, well, not whenever, but many situations where you're using infinite series and you're trying to establish their convergence. The ratio test is a very strong candidate as a test to use. Well, what does it say? Well, first of all, we're going to be dealing with a series with positive terms. Later on, not in a long time, we're going to find out that this is not really such a great restriction. Okay, we can always reduce to this situation because of something we're going to learn later. But for now, again, we're looking at a series with all with positive numbers. Well, it turns out that a series like this is convergent if the limit as n goes to infinity of the ratio between consecutive terms of the sequence turns out to be some number which is less than 1. Okay? So if that limit turns out to be some number which is less than 1, then the series is going to be convergent. The proof is actually amazingly simple. Well, not totally simple. Follow me. Okay, just stay focused. But it's not very complicated at all. It does not involve any very complicated mathematics, but it does involve some of the things we have seen before. Let me start with some couple of fairly basic considerations. We want these things, or we're assuming that this limit is some number L which is less than 1. Okay, if L is less than 1, then L plus 1 is less than 2, right? I mean, that's fairly simple, right? And that means that L plus 1 divided by 2 is less than 1. Now, why am I doing all this? Because we're going to need that number, the L plus 1 over 2. So we're going to give it a name. We're going to call it R. Okay. Does the notation suggest where we're going? If not, just hang on. Now, also, the fact that L is less than 1 implies that L over 2 is less than a half. Okay, so far so good. And that implies that L over 2 plus L over 2 is less than L over 2 plus 1/2. I'm just adding L over 2 on both sides. Now, what do we have on the left-hand side? Well, L over 2 plus L over 2, well, obviously that's L. And what do we have on the right-hand side? Well, we have L plus 1 over 2, which is what we called R, right? Alright, so what that means is those ratios will have to converge to a number L which is strictly less than this number R, which means that at some point, from some point on, let's call that some point on capital N, for any index n larger than that place, so eventually their ratio is going to be less than R, right? Because it's going to have to go towards L in order to converge to L. At some point it will have to go below R and stay there, right? So that's what we're going to do. We're going to say at some point the ratio between those two numbers is going to be strictly less than R, which means that an plus 1 is going to be less than R times an. Okay, if we are not already at capital N, we can play the game again. Now an is going to be less than R times an minus 1. And we can keep playing this game until we reach down to this number n where we could first make that claim. But notice what we're doing. We're saying that the series we're working with is less than a geometric series indicated by the power of R times this beginning number where the eventual part begins. And therefore, if you compare these two just by a direct comparison test, we can say that our series is less than a geometric series. And what is the ratio of this geometric series? It's r, and we found out that r is less than 1. Therefore, our geometric series converges, and our series being less than that geometric series is going to converge again. Okay? So again, you may want to review this proof again, and not very complicated. Maybe the only place where you have to think a little bit carefully is the interpretation of this eventual situation, the fact that from some term in position capital N, from there on we can say all this. All right, but once that is cleared and is out of the way, then basically what we're saying is that our series under those conditions is going to be less than a suitable geometric series. Now the flip side of the ratio test coin is that if we're dealing with a series with positive terms, okay, if that same limit is a number L which is greater than 1, then we can say for sure that the series is divergent. This is even easier to prove, okay? Because in this case, if every number, once you take the ratio with the previous one, ends up being eventually some number which is greater than 1, it means that the thing is going to be increasing and positive. So that means the sequence itself cannot possibly have 0 as a limit, which means that the divergence test applies. Okay? So just recapping, we're looking at the ratio of two successive terms of the sequence. If the limit of that ratio is going to be some number greater than 1, it means at some point the sequence is going to be increasing. It's increasing positive. It cannot go to 0. If it doesn't go to 0, it diverges. Fairly simple. So the ratio test works if that limit exists and is less than 1. We know what happens. If it exists and is greater than 1, also we know what happens. Well, what if that limit is exactly 1? Well, unfortunately, in that situation, we're left out stranded, because in this situation, the test is inconclusive. And to convince you of that, we're going to see in class that, in fact, all P series, if we apply this ratio test to a P series, we always end up with 1 as the limit. And we know that some P series converge, some diverge. Okay? So that tells us quite clearly that it's inconclusive. We don't know what's going to happen.